atomic. All right, so last time I finished up the chapter 7. Basically, what you need to do is try to remember cover cation. And if it's more substituted with the alkyl groups, it'll be more stable. So maybe you can have much more stable than this one. So this is the kind of reason why you brought up to whenever you have something like this one, you're going to have products looks like this one rather than this one, because this is where you can find the more stable position of the carbocation than this one, because this one has only one primary carbocation, it is secondary. So we'll try to make the carbocation not in the middle, not the end. This is where you can have bromine can tag that potential on the carbocation. So that was pretty much everything about most of the second half of chapter 7. Same thing goes with the double bonds. If there's more substitute double bonds, you have a more stabilized the alkene groups. Probably because of the similar reason. The only one thing that only one more thing I want you to know is the hydride. So among these two positions, the carbons in the double bonds, obviously this is better position because it has a secondary, this one has only primary. So instead of putting the carbocation in here, I'm going to put it here. This is the better choice than this one. So I'm going to choose this one because it has more stability. So they comes into bromine also tags and this type of, this is kind of repeat, that's why I'm kind of doing this very briefly, but this one, but sometimes this hydroxide means they're going to move hydrogen with a pair of electrons on here to make an even more stabilized carbocation position, which you actually have, this is now secondary, it's actually tertiary now. So this is why they're doing hydroxide to make even more stable carbocation compounds there. And now, eventually, they can make this one, along with a little bit of this one, but this will be more is a product from this one. This is what we call hydroxide. So this is kind of exceptional case from later part of chapter 7. So please watch the Monday lecture on YouTube channel again. So this is a quick review for chapter 7 at very last part. I'm doing this again before I move into chapter 8 because you see the reason why it's in. So, so chapter 8 now, it's quite about how you're gonna utilize the alkene groups here. So if you have a double bond in somewhere, whatever the R groups or hydrogen doesn't matter, you're going to have some type of X and Y. So maybe the hydrogen, halogen, or some other any combination of two elements X and Y. Okay, so just plus something here. And then they can go to alkene again by having those two groups here. So this is why we can call this one forward reaction or the addition. But if you think about in a backward, if you have two groups on this carbon, these two carbon, maybe you can eliminate those two to make back into the alkene form again. So then the reverse, or you can say back reaction will be elimination. Kind of makes sense, right? Okay. So what you can do is with this one is one example I can give you is this. If you have the bromo cyclohexane, what you can do is you can try to use some base, like a potassium hydroxide is the good one. And then you can also try to put it in the ethanol here. This is so what you can do is whenever you have some reactants here, or the catalyst goes on the top of the arrow when you try to represent the reactions. The one on the bottom usually is solvent. So this is like an environment where this reaction is happening. So we chose the solvent molecule, this ethanol, and this is the one actually gonna do some chemical reactions here. So if this is the happening here, your product outcome is looks like this one. Okay. And then the byproduct is water, and then potassium. Okay. So what happened really is you don't have to know what happened now. This is actually kind of preview from the later chapter. If you look at this one over here, you know there's the hydrogen over here, right? The base from this one, right? The potassium hydroxide has the potassium cation and this hydroxide here. So they're going to have, they're going to grab this one because it's the base. So the one on the lone pair of the oxygen will try to get to the hydrogen, it goes up here, and this bond here now goes up to there. So what happens is hydrogen taken to the base, which is hydroxide anion. So they become water. And the pair of electron now is nowhere to go onto the double bonds. Okay? And then now it's kind of electron pair movement and push this one to this one, which is quite good living group because it's also taking electronegative, right? It's quite electronegative. They can easily take the pair of electrons over here and they're left as bromine anion. So later you can pair with this one with the potassium cation. This is why we have this one. So this is just a good example of elimination. You can try to kind of see. So here, what might be the X and Y here? It would be just hydrogen where the other things. Okay. Kind of makes sense, right? Okay. All right. So there's one more thing I can give you. Over here. So what you can do is you can try to do sulfuric acid here, okay, and water. And in here we're gonna use the THF. This is the tetrahydrofuran. It looks like this. Okay. This is a very common organic solvent. So there's a lot of reason we're using this one, but normally this can be usually well used with water. That's why it's using over here. So if this is the case, you can just try to. That's what happens here. So think of same here. Actually, this is the. Let's assume so. Always, I don't show really hydrogen on the skeleton structure. So you can assume there's two hydrogen over here, right? This is the, the tetrahedral structure. So this one has here is a eliminate here. So now you have everything right here. Okay. So this is another example you can see in chapter 11. So basically what I'm saying is whenever you have some groups on the compounds, maybe in the arcane, you eliminate those groups, you can have this alkane group over here. The other way, you can add some XY form, like either anything. You can have an addition of these two elements on the carbons, or previously in double bond. Now it can be in arcane form because the addition of these two. Makes sense, right? Just the basic idea here. Okay, so the first part of chapter 8 is the halogenation. As you can see in the periodic table, you look at the group 7. We have a lot of halogens over there. So this is like a halogen addition, right? XY is simply just halogens here. So we have, fluorine, bromine, chlorine, and iodine, and so forth. We normally only do these two. The reason is the fluorine is too reactive. So in industry and research, they don't really can control how it works. So we don't normally use this one. And this one is too like a non-reactive. So normally we use bromine and chlorine for halogenation of the alkene. So I can give you one example here. So we have some cyclopentane over here. So if you look at this one here, and I'll try to kind of show you more like a top side view, but it's more like a 45-degree upon the plane. So it looks like this. You can see it. So this is maybe top to bottom view. You'll be more like looking at like a 45-degree here. So this should be more like a more thinner this way in the talking about. But so if this is the case, what we can do is we're gonna do it with the bromine. Obviously, gonna end the diatomic form here because it's unstable as a mono. So if that is the case, what happens here is let's say we have this one comes in the one side. Okay, so if you look at this cyclopentane, you have up and down, right? Face up and face down. So let's say we have this one comes into this side, maybe bottom, the side of the ring structure. And then, as you know, the one in the double bond can be tacked here, kind of like a nuclear attack here. And this one also can attack here. So then that goes to this one. So what happens to this one is now goes to like this one. And there's the one that's break apart as an anion. Because the pair of electron now donated here and goes up and down over here. Okay. Kind of makes sense. So you have this type of form here, which is there's all groups on this bromine here. So this is what we call this bromonium ion. Bromonium ion. Because it's a positive charge, this is kind of ionized. But with these two R kind of groups over here, so it would be R2 bromine plus. So we call this bromonium ions, and this is kind of common form you can use for almost any kind. Because those two as kind of an R group here. So if that is the case, you still have this one to attack, and one of the here. So let me draw this one over here again. So now you have bromonium ion made in the bottom, right? So you have other nucleophile here is looking for the chance to attack. So if this is already formed on the bottom, this is only can attack the one of the tops from the top, right? So you can actually, whenever it attacks, this one of the bonds breaks, okay? And then it goes to this one, and just that the carbocation we withdrew this pair electron as a nucleophile, right? So I think this is kind of happening almost the same time. Okay. So if you look at this one now, this one on the top, the other on the bottom here. So the bond to the this bromine is actually heading up phase from this previously double bond plane, and the other was oriented now at the heading downward. So this is a ring structure. Now your double bond is gone, but still you cannot rotate, right? So you can still call this trans. So because of formation of bromonium ion, while you have a halogenation process, the thing is they're all going to be added onto the double bond, the opposite directions, right? You see that, right? So we call this anti-stereo chemistry because they're only going to be added on to this double bond on the opposite positions, opposite phase. So this is why we have a kind of this anti addition here. Kind of makes sense so far. We good? Do you guys see why it's forming an anti-position? Right? It's happening. So why the other bromine going to attack? They are the ones already occupying the bottom, so they can actually attack here, but they attack on the other face.
How does the double bond just go?
Oh, so the as you can review in the chapter 7, the electrons on the pi bonds have a more accessibility to the outward because the sigma bonds were in the middle between the bondings is so tightly held to each other. So the one on the pi bonds, so there's a two bonds, right? In the double bond, you have a one sigma bond in the middle. You have a pair of electron kind onto the p orbital in a more vertical way. So those two make a pi bond, but obviously it's much easier to use the electron here than here to make any additional bond if they wishes to. So normally in a double bond, the pair of electrons in the pi orbital, they're going to kind of work as a nucleophile. So we call this nucleophilic attack. This is also what happened to this bromine here. So this is kind of this is kind of how it happens. So now once it's used up to make the bromonium ions, sorry, that was actually, now I see where you come from. So now it's just gone. Okay? So now and then you're going to have a carbocation form once you get break apart on this side, but it's going from other positions. We good, right? So actually scientists actually kind of wonder if that is really exists, because if you think about bromonium ion form, it's very unstable. So they tried to prove this one, and they found the actually article published like 50 or 60 years ago. they actually made the bromonium ion separately from using antimony pentafluoride with the bromo alkene. So that was indeed for real deal. We believe so far, as halogenation is happening anti-tariff. I can move on, right? Can I? Okay. So the next one is what we call halohydrine formation. So we call this a halohydrine. This simply looks like this. If you have any double bonds, makes the alkene, right? And if you have actually a combination of halogens and also the water, they can actually form. Maybe here, looks like this. So only difference between these two is either they're going to do two dihalogenation, but it's more like this hydroxy group and the halogen over here. That's pretty much it, the difference over here. So I'll show you one example here. What I can do is so this is simply trans like 2 alkene, right? So 2-15. So this is the maybe this alkene compounds. Let's say we have bromine and water. So what happens to this one is it's pretty much the same. If you look at this one and here, they're going to form bromonium ion. Okay. This is the here. So if that is the one you already have, that water comes into this side here, not on the, because this is already occupied on this side, right? So the water kind of. So if you look at the water here, do you know there's a 2 lone pair over here, right? Because the oxygen is group 6, right? So there has to be 6 valence electron, but there's only 1, so it'll be 2 lone pair over here. You see it, right? So they can actually make attacks on here as because of on this side. So that makes like this. Okay. So if this is happening, this is a particle choice. Because now it's neutral water, but they're donating a pair of electron to this carbocation, and then they're going to have this bond is gone because carbocation is got an electron donated from the water, but water now is missing 1. So that what happens next is now the water comes, and then it grabs this one. Oh, no, sorry. The other one. Grabs onto this one. So it goes onto this one. Oh, sorry. Not here. Here. So if that is the case, you can have like this. So one hydrogen is taken to the other water, And now the paired electron over here is going to this positivized oxygen. It's now become neutral. Kind of makes sense. So this is very similar to halogenation, but just the only different part is once you get to bromonium ion formation, the later one was not the other bromonium anion, but was just the water, kind of do as this one. So it's also kind of going into the opposite direction. Kind of makes sense? We good? Any question? We good, right? Okay. Looks great. All right, so okay. So the next part is the hydrate. So hydration simply means you're going to have you just add a water. Okay? Just add a water here, and then you're going to have this one. This one. Okay? So as you can see, this H2O, the hydrogen, which it's H2O same. So you just the hydrate simply means you're going to surround the carbon with the water. So we call this hydrate. Okay. So I'll give you one example here. So if you have a double bond over here. If this is the case, we normally do that with some strong acidic solutions. Okay? So you just see this one has a very strong acidic solution over here. Okay? And then whenever it comes to one over here, it grabs the carbon over here, right? Once again, double bond. We'll try to grab. So they're going to use the pair of electron on the double bonds to grab. The one in the hydrogen is this one. Do you guys remember what this is? It's a so the Arrhenius definition, you have a lot of protons, right? That will make your acidic condition, right? But if you use a Bronsted-Lowry definition, you have to deal with water. So the hydrogen cation, hydronium cation is pretty much the same thing. Kind of makes sense. So you can think this as just like a protonated, like water, but protons. It's pretty much the same thing. That's why we're using acidic condition over here. Makes sense, right? Okay. So if it then opens up to this one, the double bond is gone, because of the hydrogen over here. Okay, and then whenever you have a so if they're all making here, this is where you find the carbocation. Okay, because you only have a 1, 2, 3. Okay? So in here, water is actually looking for chance to look for a nucleophile. And so it kind of work as a nucleophile. So this kind of goes to here, and carbon here is kind of work as like electrophile. Something look for some like negative, something negative. But so you kind of wonder why water is not negative, but it's kind of looking for here. It's because of the relatively speaking. So carbocation is now positive. Now this water can take this one over here. So what happens to this one? Is it my drawing okay today? It's good? Okay. You see this one, right? It's pretty much the same what we did before. Yeah, because you're right. So in here, the same thing happened again. So this is, obviously this is very unstable, right? This is very unstable. So try to grab this one. Goes over here. So this one will become, it's just the same what we did just before. This will become this one again, right? And then this one becomes hydrogen. So you see now hydrogen. It's pretty good, right? So whenever you do this one, it doesn't really bound by anti-bromation anyway, because you don't see any bromonium ion over there, right? Formation. So it doesn't really bound by stereochemistry anymore over here. I think this is good. So you see, first time when it comes to the first attack from the double bond, you have this one, and now as an outcome, you also have at the end you also have this one. They're the same, right? So there's no change on this one. So this is what we call acid catalyst. So catalysts, in definition, they don't change over the reactions. They can be only used, but at the end they're just the same form. But it only makes the reaction goes much faster. That's pretty much it. Kind of makes sense. You good? All right. So I have several more things to go, but I'll just stop here today. So I'll try to finish